Hello everyone. Today we are going to be talking about Mohr circle and going through an example problem. So we are going to go through this problem. A point A in a structure figure 1A is subjected to the in-plane stress state shown in figure 1B. A. Use the stress element in figure 1B to draw the Mohr circle on the graph paper. And use the Mohr circle to calculate I, the principal stresses in the xy plane. 2. The maximum in-plane shear stress and its direction with respect to the x-axis. 3. The absolute maximum shear stress. 4. Draw a stress element to show the in-plane maximum shear stress correctly oriented with respect to the x-axis. Part C. Use the Mohr circle to calculate the normal and shear stresses in the xy directions. Note, the x-axis is oriented at a 30 degrees counterclockwise from the x-axis as shown in figure 1b. Use the Mohr circle to calculate the smallest angle theta 3 from the x-axis where the normal stress is sigma x double prime is equal to 22 ksi and indicate the direction clockwise or counterclockwise of theta 3 from the x-axis. So basically, first we're going to start by calculating the principal stresses in the xy plane because that is going to help us graph our Mohr circle. So as we see over here, to calculate the principal stresses in the xy plane, we have basically sigma y prime, and we can call this sigma x prime, and theta and sigma average here is going to be equal to sigma x prime plus sigma y prime over 2, which is equal to 30 ksi plus 10 ksi over 2, which is equal to 40 over 2, which is 20 ksi. Our R value, which is going to give us the radius of the circle, and the 20 ksi gives us the center of the circle. The R value is equal to the square root of sigma x prime minus sigma y prime over 2, all together squared, plus tau on the shear stress on the x face in the y direction. So tau xy prime, I guess we were gonna call this squared. And R is equal to, let's see, well, we don't have a shear stress in this diagram since we only have axial stresses, 10 ksi and 30 ksi. So the shear stress is equal to 0. And we can simply plug in our values for sigma x prime and sigma y prime. So we get sigma x prime is equal to 30 ksi, so 30 minus 10 over 2 squared plus 0. And that is simply equal to the square 30 minus 10 over 2, which is 20 over 2, which is 10. So our value is that. So our principal stress 1 is equal to and I'm going to call this sigma average. Okay, yeah, sigma average is equal to sigma average plus R, which is equal to 20 plus 10, which is equal to, and this in KSI, 30 KSI. And our principal stress 2 is equal to sigma average minus R, which is equal to 20 minus 10, which is equal to 10 KSI. Um, and basically, these two principal stresses will give us the information needed to start a graph of our Mohr circle. So we can draw our Mohr circle down here. And the Mohr circle is a graph of, by convention, tau is on the lower axis and sigma is on the positive right axis. Um, so this means that our sigma average is going to be at a value of 20, just going to be named here. So the sigma average, and then sigma principal stress 1 is going to be at 30 KSI, and principal stress 2 is going to be at 10. So we have a circle connecting these points. And this is going to be our Mohr circle. So step 1 is completed. We calculated the principal stresses, and now we want to calculate the maximum in-plane shear stress and its direction with respect to the x-axis. So the maximum in-plane shear stress is always given by R, is always equal to R. Um, and it's equal to 10 KSI, as we see from R over here. And oh, we want to know its direction with respect to the x-axis. The x-axis is over here. So now they're asking us to calculate an angle. Which is going to be so to calculate the direction of the maximum in-plane shear stress with respect to the x-axis, we're going to have to see how the stress element is rotated in order to end up at y prime x prime. So as we see, we went counterclockwise 30 degrees. And on our Mohr circle, all the angles are doubled. So here we have our over here, this is our uh x prime y prime axis, and we want to rotate it until it is at yx. So where is yx going to be? It's going to lie at 2 times 30 degrees. So 2 times 30 degrees is equal to 60 degrees. And since we rotate the element counterclockwise, we rotate also counterclockwise, but here by 60 degrees in order to end up at our yx axis. So 60 degrees about looks like this. And it's uh, through the uh, center of our circle. So here we have the x and we have the y. And this is by 60 degrees. Um, so they want us to, they're asking for the maximum in-plane shear stress direction with respect to the x-axis. So I guess what they're asking for here is because the maximum in-plane shear stress is going to lie how? So in order to solve this problem first, we have to know where Tmax lies on the Mohr circle. Tmax lies at these two extreme points of the Mohr circle. So here it is Tmax, oops, one, so tau max in plane. So essentially they're asking us to find this angle over here, which we will call um theta theta prime. But it's actually 2 theta prime because theta prime will be the angle on the stress element from between the in-plane maximum shear stress and and the x-axis. But remember that everything in the Mohr circle is doubled, so we have to double that angle. And what is this angle going to be? It's going to be so basically if we write over here uh so 2 theta prime is going to be equal to 180 degrees and minus 60 degrees, which is equal to 120 degrees, and thus theta prime is going to be equal to um 60 degrees. Is that correct? Let me check. Wait, hold on. I did something wrong. The T max in plane is actually vertical, so it will not be that angle over there. So it's not this angle that will be 2 theta prime. It is rather, um, let's draw a dotted line. The angle between the x-axis, which is this axis over here, and the vertical line, because we're calculating the distance between the maximum in-plane shear stress and the x-axis. And then this one will be equal to 2 theta prime. So 2 theta prime would be equal to this is 60 degree plus 90. Is it 60 degree plus 90? Yeah, I think yeah, this one is 60 degree and this one is 90 degrees. So 60 degrees plus 90 degrees, which is equal to 150 degrees. And thus theta prime will be equal to 75 degrees. Um, so this will be our answer for, well, no. Yes, this will be our answer for part two, its direction with respect to the x-axis. And notice that with respect to the x-axis, we went counterclockwise to arrive at the x-axis. So this means that from the shear stress element, we will rotate 75 degrees counterclockwise on this stress element to arrive at the shear stress. Oh, or no, we would rotate 75 degrees counterclockwise from the shear stress to arrive at the x-axis, and thus 75 degrees um, clockwise from the x-axis to arrive at the shear stress. So 75 degrees will be around like here. 75 degrees would be around that, I guess. Or not really, because that one is 30 degrees already. So be somewhere over here. 75 degrees. Wait, how come that looks larger than 90 degrees actually? So it'll be, I guess, the 60, it'll be somewhat a little less acute. Yeah, so about that. So now for part three, we're asked to find the absolute maximum shear stress. So the absolute maximum shear stress um, is given by the equation the largest value of stress minus the smallest value of stress um, over 2 is equal to the absolute maximum shear stress. And sigma 1, by definition, sigma 1 is always greater than sigma 2, is always greater than sigma 3. And you might be thinking to yourself, this is a 2D problem, so we will not have a sigma 3. So where does that sigma 3 come from? Well, in a 2D problem, since we don't have to deal with sigma 3 is automatically just 0. So our outer plane Mohr circle will look something like this. I guess that looks approximately like a circle. Uh, But then our sigma 3 value will be 0. So our Tmax absolute value would be simply sigma 1. And sigma 1, since it's always the maximum value, over here it happens to be equal to our principal stress value 1. So we'll use 30 KSI for sigma 1 and 0 for sigma 3. So um, Tmax absolute will be equal to 30 minus 0 divided by 2, which is 15 KSI. So that is our Tmax absolute value. And now for part 4, we want to draw a stress element to show the in-plane maximum shear stress correctly oriented with respect to the x-axis. So part 4 is kind of referring back to um, these two parts of our previously calculated entities. And also the Tmax absolute is basically this location over here. Basically the kind of vertex of this larger circle. So to draw a stress element to show the in-plane maximum shear stress correctly oriented, we note that we rotated from the x-axis we rotated clockwise by um we rotated clockwise by 150 degrees in order to end up at our T max in plane. So the actual stress element will have to be rotated 75 degrees with respect to the x-axis to end up shear at our max shear stress in plane. Thus, the stress element will look something like this. Um, 75 degrees is about, from the x-axis is about, let me see, about like that. And okay, it will be kind of perpendicular to it, so that's our stress element. And our x-axis is going to be lying like here. So these are x. And oops, I think I'll draw it better. So yeah, so this is 75 degrees cl clockwise. And our shear stress is going to be, let me see, our shear stress T max in plane is positive because well, our sigma x value over here is basically 20 and it's equal to our sigma y value. Because if we draw a line through here, oops, and we'll just call this to distinguish it from other ones, we'll call it x double prime and y double prime. So they lie across from each other. So the x double prime is equal to y double prime. Wait, sigma x double prime is equal to sigma y double prime because sigma is this x-axis over here, or horizontal axis, I mean. So they're both equal to 20 KSI. So we we know they're both equal to positive 20 KSI because the 20 lies to the right of the origin. Um, so it'll be in tension, at least we know that much. Um, so we can thus draw some arrows in tension. I'm trying to draw them perpendicular to the stress element because that's how they should look. This one should be 90 degrees, just so you guys know. And each of this is 20 KSI. And this one is the sigma x double prime. And this one is the sigma y double prime. Because we rotated 75 degrees from the x-axis to end up at our stress element orientation. And is our stress value going to be positive or negative? Well, tau xy double prime. So tau xy double prime is basically the shear stress on the x face in the y direction. So on this stress element, it'll be like the shear stress on the x double prime plane in the y double prime direction. So it'll be pointing up since the shear force corresponding to our x sigma double prime is actually positive because it lies to the bottom of the origin. And according to our convention, tau here is positive. So it'll be pointing upwards. And then we use the head-to-head, tail-to-tail method to complete the shear force, to complete the shear forces. And the value of this tau xy, so it's tau xy double prime is equal to the maximum in-plane shear stress, which is 10 KSI. Some of this stuff is really tricky, so I hope you guys are following along. If you're not following along, feel free to leave comments in the comment section and I'll respond to them whenever I can. Um, hopefully soon. Draw a stress element to show the end-plane maximum shear stress. Yes, we did that. And use the Mohr circle to calculate the normal and shear stresses in the XY directions. Note the x-axis is oriented at 30-degree counterclockwise from the x prime axis as shown in figure 1b. So this one is kind of the reverse of part 4 of part B. So I've kind of zoomed in on the Mohr circle to get a closer look at it. And we want to find the normal and shear stresses in the XY orientation. So the normal stress will be basically um, the coordinate of this point over here, um, this point over here, with relative to the origin. So it will be this position. That would be the normal stress in the x direction. So it will be, let's call it sigma x. Sigma y, on the other hand, would be, since y is located at this distance, it will be kind of, if we draw, this is a straight line. This is a straight line, and this is a 90-degree angle. So it will be this distance from the origin. And then the shear stress would be the corresponding vertical distances, which would be the same since this graph is symmetric. So the tau xy would be this vertical distance, and tau, I believe tau y, also tau y, yeah, they're all tau xy. Tau xy would just be this vertical distance and this vertical distance, which have the same magnitude but different sign. So we can calculate first the vertical distance, since that seems easier to do. So to calculate the vertical distance, we can use, well, we know this angle over here is like 60 degrees, this angle over here of the triangle. So we're basically looking at this triangle over here, this triangle. And this triangle has a 60-degree angle, and sine of that angle is the vertical distance over the R value. So we can state that sine 30 degrees, sine of 60 degrees, I mean, is equal to the vertical distance, which is sigma, which is tau xy over R. So basically, R times sine of 60 degrees. Yeah. R times, okay, sine of 60. Yes, R sine 60 degrees is equal to tau xy. And our R value, as we calculated from before, was, I believe it was, let me check. Yes, our R value was 10 KSI. So over here we have that tau xy is equal to 10 sine 60 degrees. So it's equal to, okay, what is that value? Well, make sure your calculator is in degrees. And we have sine 60 times 10, which is equal to 5 root 3, which is approximately equal to 8.66 is what I'm getting. Oh wait, and don't forget that actually this is equal to negative tau xy, since the vertical distance is like is on the top side of the horizontal axis, and our convention tells us that tau, the bottom axis, is actually the one that is positive. So we have negative 10 sine 60, which is equal to then negative 8.66 KSI, kips per square inch. And then we have to calculate the horizontal distances, because this tau xy value is kind of symmetric, so the magnitude is going to just be the same here, except it's going to be positive. But in order to calculate the horizontal distance, we first have to find this little distance here. So to do that, we'll use our cosine, since cosine relates adjacent to hypotenuse. And in this case, our adjacent is the distance of interest, and our hypotenuse is the R value. So we will use R cosine of 60 degrees is equal to our distance of interest. But note that this is not equal to our sigma x value. Sigma x value is going to be um our sigma x value is going to be the distance from the origin to that point. So we're actually going to have to add sigma average. Wait, or not sigma average even, but we're going to have to add yeah, sigma average plus some value. What is that value? Okay, well we know that our principal stress one is at 30 and our principal stress and our sigma 3 is at 0. So the radius of this large circle is 15. Yeah, wait, actually, I figured it out. Never mind. The sigma average is what we are going to have to add to this distance over here, since the sigma average is actually already telling us its position in the horizontal axis. So our sigma average is at a location of 20 units to the right of the origin. And adding this distance will give us the distance from. Okay, sorry. So as I was saying, so R is 10. So 10 and then cosine 60 is going to be 1/2. So times 10 is equal 5. R cosine 60 is equal to 5. And then we will add that 5 is this distance over here. So we would add 20 in order to get the distance from this coordinate to the origin. So 5 plus 20 will give us that sigma x is thus equal to 25 KSI. And since we already know that this distance is 5, sigma y, which is the distance from the origin to this point over here, should not be that hard to calculate. So sigma y will be equal to sigma average minus 5, which is then equal to 20 minus 5, which is 15 KSI. And both of them are positive because they lie to the right of the origin. So for part D, they want us to use the Mohr circle to calculate the smallest angle theta 3 from the x-axis where the normal stress is sigma x double prime equal to 22 KSI and indicate the direction clockwise or counterclockwise of theta 3 from the x-axis. So we kind of already called something theta double prime already. So we can call this, I guess, theta x triple prime, just so that we don't get confused. So, okay, we have to use the Mohr circle again to calculate the smallest angle. So where the theta x is 22 KSI. And we need to indicate the direction clockwise or counterclockwise of theta 3 from the x-axis. So let's zoom in on our Mohr circle again. So if we think through this problem, basically, we found that this value was, oh wait, I'm gonna change color to make it more visible. So let's choose like a pink or purple. Yeah. So we already knew that this distance was 5 and that this distance was 25. So we know that 22 will lie somewhere here. And it will be when the angle is kind of like this. And when they say smallest angle, they're just talking about, so smallest angle clockwise would be going, smallest angle clockwise would be like this. Um, and you probably would not want to choose the uh, y-axis here. Yeah. Because sometimes the clockwise angle gives you a smaller angle than counterclockwise angle. So they just want you to express it in terms of either clockwise or counterclockwise. Um, so how can we go about approaching this problem? So now we kind of have to work backwards. We're given the distance as 22, and we know that the sigma average lies at a distance of 20. So 22, which would be the distance we are interested in, minus 20 is equal to 2. So 2 is the distance here. And we know that our R value is not going to change. So this is just working backwards. It's here we can use cosine. So our cosine, uh, arc cosine of adjacent over hypotenuse, which is here 2 over R, which is 10, is equal to 2 times theta triple prime. And it's 2 times theta triple prime because this angle that we're going to find is actually double the angle that we would need to rotate our stress element. So from that, we get that theta triple prime is equal to... Wait, actually, I think our process for this is wrong. For this, we're only finding the smallest angle between x prime and x, but they're talking about a whole different axis, actually. They're talking about if we kind of have another axis, which is like x triple prime, uh, y triple prime. What is the smallest angle at which the x value corresponding to that is going to be 22? But we kind of, I guess we kind of do know something about how the axis is oriented because we know that we know that x triple prime is going to have to be somewhere to the right of this line over here because at this line we already have 25, so 22 is smaller than that. So it must be something like this, where this is x triple prime and this is y triple prime. Sorry, it's very messy now. But basically we want to find this smallest angle between x and x triple prime. And since everything is doubled on the Mohr circle, it's this angle that will be called a 2 times theta triple prime. So first we have to find how to express this angle. So this angle can be expressed as as this angle here. This angle here is very hard to see. So basically, this angle here is the angle from the x prime axis to the x triple prime axis minus the 60-degree angle. And we can basically find the angle between x prime and x triple prime by using triangles. So, how am I gonna do this? Okay, I'm gonna draw a clear picture down here. So we have this slope and this slope. And then we can note that the R value always stays the same. And that this distance over here must be equal to 22 minus sigma average, which is equal to 22 minus 20, which is equal to 2. So thus, the angle, this angle, which is going to be, this angle is going to be basically arc cos of 2 over r, which is 10, which is equal to 78.46 degrees. And 78.46 degrees minus 60 degrees is going to be our smallest angle. So 78.46 degrees minus 60 degrees is going to give us 18.46 degrees. And we go counterclockwise from the x-axis to the x prime axis. Um, and this is counterclockwise from the x-axis to the x prime axis. But we're actually not done yet. This is our 2 theta triple prime. So our theta triple prime is going to be half that, which is 18.46 divided by 2, which is 9.28 degrees. So this is our smallest angle. And again, it's going counterclockwise. So on the stress element, it will be counterclockwise by 9.28 degrees because on the Mohr circle, it's counterclockwise by 18.46 degrees from the x-axis to the x prime axis. Sorry, I read my calculator wrong. This is supposed to be 9.23. All right. Well, I think all of our parts are finished and I'm going to give you an overview of everything we did. Oh yeah, and also it's worthy to note that 9.23 degrees is counterclockwise from x to um to the x triple prime axis. All right, I hope this video was helpful for you guys and stay tuned for more updates. And leave any questions or concerns in the comments and I'll be sure to respond to them. Thank you guys for watching.